Okay, we are starting 5.3, probably finishing 5.3. 5.3. And you know, there's test on Friday, the usual, right? Where you can pick it up. I'm trying to think, yes. And yes, so, and then you can bring it to eLab.
Yeah.
Wait, oh, no, I'm gonna be at vector space. Uh,
You
Try to-
can do the slide you can put it on the.
yeah, yeah,
1:15
1:15, yeah. And I'll, if Sheldon's gonna be around in his office, I'll just have you drop it off with him. I'll ask if he's gonna be around or not, but. Okay, this is Ampere's law finally. No more of this nastiness like we did. That was fun. But we got to do it, right? So you see what a deal you're getting for Ampere's law. Okay.
I would take it at face value.
Yeah. Okay. Okay. All right. So really, we're going to cover the divergence and curl of B, but it's going to get us to Ampere's law, okay? Because we're going to also look at the divergence. All right. So if we recall that if you have a line of current, so let's say I is coming out of the board here, that the magnetic field is going to look like these circles. Now, of course, it's not really circles, right? It just means that the magnetic field, vector field is turning. The little vector fields arrows are turning, right? In a certain direction. And this really does kind of look like a field where you should have a non-zero curl, doesn't it? Okay. So we expect maybe we're going to have a non-zero curl. Well, let's look at, we've done this problem. We know that B is equal to mu 0I over 2 pi s, where s is the distance. And I'm really sorry, those don't look like circles. It's really terrible. Let me see if I can just move this so it looks a little better. There we go. So it's in the center. Okay. And then s is just this distance away. Yeah. And it's in the direction of phi hat, right? If phi hat is in this direction, right? What would you expect it to be? Right? So this is in the direction of phi hat. Okay. So we know that if we take let's look at the curl equation. So I'm going to do the integral over a surface of del cross B dot ds. Or that should be dA. What am I writing ds for? Don't know. Then this is going to be the integral of B dot dl. Right? Well, what is that? Let's write that out. We know what B is. So we have the integral, and this needs to be a closed curve that bounds the surface. And so we have mu 0I over 2 pi s for our thing and our B field, and then dl, and that's of course just mu 0I over 2 pi s, the integral dl. Yeah. And 2 pi s is the integral dl, right? That's the length of a circle as you it's the circumference of a circle. Okay, so this is just going to be just mu 0I, which is what we expected. So we see that there's something here, and notice that this I is the current that's kind of piercing the surface. If you think about the surface as being, something like this, right? And then you have this loop at S that we think about, yeah? I mean, that's just drawing up the B field, but it might as well be a loop, right? Because the path we just integrated upon. So we have a current that's kind of piercing the surface that's bounded by that loop, yeah? And so this is a hint to the first, to where we're gonna get Ampere's law. Okay. All right. Now, let's look at a case where we don't have any current in a loop. So if I said, let's look at something like this, and you have a wire here with an I coming out, right? And then let's say we have a loop somewhere else. Okay, so here's a loop. All right, well, if we think about how to integrate that loop, right? Notice, by the way, we probably should have written it here, but we're integrating this DL. We were a little fast and loose with that. We're integrating that. What's happening here is it's d phi, right? And so that means that DL here in our previous problem, which we should have, again, been a little more careful, but DL here was going to be our DL phi, right? And that's S d phi. So really this integral was, this guy was the integral of S d phi 0 to 2 pi, right? That's how we got 2 pi S. Okay. So similar thing here, we're going to integrate between this phi 1, and phi 2, right? Okay. But think about what's happening right in this loop. So say we start right here, right? So that's phi 1. We're going to integrate around the loop, and the phi is going to change, changing phi, changing phi, changing phi. It gets up to phi 2, but then it goes right back to phi 1 to get back to the beginning, right? So that integral is going to be 0, right? So the integral here, the integral around this loop, so let's call this P1, P1 is going to be 0, right? So if you're not enclosing an I, you don't have any, the integral is 0. So this is giving our first kind of hint. Okay, so we can sort of write down this. We're going to be a little bit more formal when we get there, but we have the integral around a closed loop of B dot DL is equal to mu 0 I enclosed. If there's no enclosed I, that integral is 0. Yeah? Okay. Fine. Now what about if you have a current density instead of just a line of charge, I'm sorry, line of current, like our example. Let's take a look at that. You good? Okay. So so that case, right, we would have the I enclosed is going to be the integral over some surface, and I'll describe that surface in a second, J dot dA, right? Okay, so this is the surface bounded by the loop, right? So you're integrating over a loop so, but you're trying to figure out what is the current that's enclosed in that. It might be this volume current, right? So think about the surface. If you have a loop, think about a loop. And you might have, and this dA is going to be the perpendicular vector that's got the area of this loop, right? So it's hard to draw. Let me see if I can draw. There we go. That's dA. Yeah. And J, the enclosed current, is going to be whatever component of that current, right? The volume current that's along dA, right? That's what's enclosed, because you might have current that's running parallel to the loop, right? That is not enclosed. You really have to think about the current as kind of flowing through that loop, perpendicular direction to the loop. Does that make sense? Yeah. But this might be, this little loop might be, part, so this is not drawn well, sorry. So this might be like part of a long thing, and this is its cross section, right? And there's a volume current J flowing through. But that volume current may have components that are not perpendicular to that that weird shaped wire or something. Right? So it's only the perpendicular component, right, that counts. And remember that the surface that we're integrating over here, this guy, that is the surface that's bounded by this loop. Right? It's not some other surface, not the surface of that wire. It's the whatever's the surface is bounded by the loop that you're using, right? In the other half of the integral, remember that we have, sorry, not the other half, the other side of the equation. Because we have the integral of this, and we should probably say, hey, this is some loop, B dot dl is now mu 0 times the integral that of the over the surface of this J dot dA, right? So these two things are bound up because this guy is the surface that bounds this is bounded by this curve. S is surface bounded by curve P. And it's a closed curve, so it can bound a surface, right? Okay. All right, fine. So let's use this equation. So on this side here, I can apply Stokes' law, right? Which I did already. I'll do it again. So I'm going to use Stokes' law. Oh, that reminds me, guys, there is an extra credit talk by Matt Stokes. Do you know him?
Yes.
Yeah. Today at 4 in Martin 323. Extra credit and cinnamon rolls. How late? Yeah, show up late. Yeah, that's fine. Yeah. Yeah, not 4:45. Huh?
You said cinnamon?
I did say cinnamon rolls. I'm gonna get cinnamon rolls from Sin City. Mhm. Okay. Okay, so let's apply Stokes' theorem here to change this green, the thing in the green box, to the integral of del cross B dot dA, right? And this is over that same surface. That's how Stokes works, right? It's the surface that's bounded by P in Stokes' theorem. Yeah, so great. So now if I write the other side of the equation over here, mu 0 over that same surface J dot dA, we can see that the integrands, they're both dotted into dA. They're both integrated over the same surface. So that means that they must be equal. So this gives us del cross B equal mu 0J. And this is our second, I believe, second Maxwell equation. Although this one here is the same thing in integral form as is this one. Right? These are all Maxwell's equation, one of the same Maxwell equation in different forms. Okay. The differential form tends to be the standard form, like that everybody starts with that. Okay, so when you go look up Maxwell's equations, most likely, unless you're looking at a really old book, you'll see them in differential form. Yeah, but you can always get to whatever other form you need using Stokes' theorem or divergence theorem or etc. Okay, but let's be more general now because we just showed that del cross B is mu 0J. I'd like to take the divergence of B. You're going to see that it's 0, but I'm going to prove this for a general B that we know from the Biot-Savart law. And then I'll do that for the cross product as well. So we're going to do a little math, try to figure this out. And to be more general. Let me see where I'm going with this. Okay, yes. All right. Let's start with the most general form of B, which is the Biot-Savart. And we're starting with the most general current density, which is the volume current density. Okay, remember that we're integrating over the prime coordinates, right? Remember the prime coordinates are integrating over the current, it's where the current is itself, right? That's R prime points to the little element of current, little volume elements of current everywhere in the whatever distribution you're looking at, right? Okay, so that's going to be important. Okay, let's use Cartesian coordinates. It's actually easier to use Cartesian in this case, which is often not the case, but here it is. Okay, so first thing we're going to do is we're going to take the divergence of B. All right. Now we explained before when we talked a little bit about Gauss's law. If you remember that Gauss's law is the divergence of E is equal to, like, I can't remember if it's rho over epsilon naught, I believe. And so that is Gauss's law in differential form, one of Maxwell's equations. And the reason that the divergence of E is non-zero is that if you put a point charge in a surface, the field lines leave, but they don't ever come back, right? But we said that if you put a magnet, right, you can't put a North Pole by itself in a surface, right? Because that doesn't exist. You break a bar magnet in half to try to get just a North Pole, you'll just get another South Pole and North Pole, right? So there are no monopoles as far as we know. So you put that in, all the lines that leave come right back in eventually. So the flux is always zero. So the divergence should be zero. Let's see if we can prove it just using some math. Okay. All right. So let's do first the divergence of B. In Cartesian coordinates. Okay, so let's recall that del is in terms of unprimed coordinates, right? Remember, over here in this integral, all the prime coordinates are being integrated out. They're gone. Do you see what I'm saying? Okay, they're gone. What's left is a function of the unprimed. So if we want to take del dot B, it's going to be del that's in terms of the unprimed coordinates. In other words, this is going to be x hat partial x, not x prime, plus y hat partial y, plus z hat partial z, right? There's no prime. If I wanted to use del in prime coordinates for something, I would probably put a prime on del, right? And that would indicate that everything needs to be prime, but we're not doing that right now. Okay, let's remember that also, let's look at omega. As we know, omega is r minus r prime. And in Cartesian coordinates, right, that's x minus x prime, x hat, plus y minus y prime, y hat, plus z minus z prime, z hat, etc. Yes? Z hat. Okay, Z hat, sorry, I said something else. Remember that J is only in terms of the prime coordinates, right? So if we're using Cartesian, this would be J of x prime, y prime, and z prime, right? Doesn't have any r's in it, right? B, however, is, as we've said, only in terms of x, y, z, not x prime, y prime, z prime, and d tau prime is dx prime, dy prime, dz prime. Because again, we're integrating over the prime coordinates. All right. So what that means for del dot B, if we look at the integral. So now if we say we're going to look at del, there goes my computer. There it goes. I got limited time now. Okay, so del dot B is going to be equal to del. Now it's not prime, right? I can bring it right into the integral. You agree? Why not? Okay. Mu 0/4 pi and the integral, and now I'm gonna have del dot, and then this vector quantity here, which is of course j cross omega hat. I'm gonna leave that r prime out of there just because it's gonna be yucky. And then I'm gonna put the omega squared on the bottom here, just to be clear that, right, when I take that del dot, the omega squared's in there, it's in the derivative. I mean, right, I have to take the derivative of that as well, and might as well just stick it under the omega hat. Right? And then I have the d tau prime. Okay. Now we have to do that divergence. All right, inside. So I'm gonna put that in yellow, and we're gonna go do this. All right. So we have del dot j cross omega hat over omega squared. Yeah. Okay. Now we could sit down and prove what this is using Leibniz-Vita tensor if you want, but I think I can just write it down. You okay with that? All right. But if you want to know why I'm writing down what I'm writing down, you would sit down and actually calculate this using Leibniz-Vita tensor here and the definition of a dot product, right? How we've done that before with indices. Okay. But let's just write it down. So it's going to be omega hat over omega squared dot del cross j, and then minus j dotted into del cross omega hat over omega squared. Okay. Basically product rule, right? But to prove that, you're either gonna go look it up somewhere, or you're going to, prove it yourself. Yeah. Okay. Now, the great thing is we can look directly at this and say, like, that's got to be 0 because j only depends on the prime coordinates. There are no regular coordinates in there. Right? So that is 0. So this has left us with just negative j dot del cross omega hat omega squared. Okay, fine. Now, okay, why is this 0? Because this is actually 0 as well. This thing. Okay, well, we know it's 0 mainly because we know that E is 0. Right? And doesn't that omega hat over omega squared look a lot like E? It's the vector part of E. Right? Because E is, KQ omega hat over omega squared. So if the curl of E is 0, the curl of that thing is 0 too. So this is 0. So this term, this whole term in yellow, okay, fine. So that means if we go back here, that was our whole thing, right? So that means that the divergence of B is 0, which we already knew from physical arguments, yeah? Okay, so this is another Maxwell equation. Okay. All right, fine. Now we've got to do the look at the curl of B, which we pretty much know is not 0 because we know it's mu 0 times j, right? But let's prove it more generally using Biot-Savart again. Okay. So let's look at del cross B. All right. Well, again, right, we can bring that cross product into the integral because it has nothing, the del is only in terms of the unprimed. Okay, so this is going to be equal to mu 0/4 pi, and then del cross our term j cross omega hat over omega squared. D tau prime. Okay, fine. So again, you can go look up or derive, because remember we now have a cross product, so a curl of a cross product. There is a product rule for that. Yeah. So let's write it out. So I'm going to now take the term here again in yellow. Okay. So we're going to say del cross j cross omega hat over omega squared. And then that's going to be equal to j del dot omega hat over omega squared minus j, oop, I don't know why I made a little j dot del acting on omega hat over omega squared. Now, there are other terms, but I have dropped them because there are other terms that are proportional to del dot j. And if you recall, for steady currents, del dot j is 0, okay? Because if you go look up this cross product of, the curl of cross product, it's like a nasty long formula, but every other term here is proportional to del dot j, which is 0. So we're just not going to put them in. Okay. Got it. All right. And even if del dot j, for steady currents, del dot j wasn't 0, del dot j is going to be 0 anyway, because it doesn't depend on the regular coordinates. It only depends on the prime coordinates. So even if it wasn't steady currents, this would work. Okay. So we're just not putting those in. All right. So we do know that one of these terms we already know, which is this guy. We know this from way back when. Del dot omega hat over omega squared is 4 pi times the delta function, right? Direct delta function in terms of omega. But we have the other term, this j dot del acting on that. Remember that j dot del is an operator. Do you remember what that means? The j dot del? Or any vector dot del? Would it be okay for me to bring this thing over here? No, that's right. It's a differential operator acting on that, right? So for instance, the very first term of this would be jx times partial x, and that has to act on all this, right? Okay. Anyway, all right, so let's work on that term. Let's see. So j dot del acting on omega hat over omega squared. Okay. All right. Let's see. Let's change our del. So notice that del is equal to the negative of del prime, right? Because if I want to change all of my variables like x to x prime, y to y prime, z to z prime, I just have a negative sign, right? Yeah, okay. So I can replace this as j dot del prime omega hat over omega squared, right? And let's just look at one component. Negative sign, thank you. Okay, so the and you could probably make this argument without changing to the prime coordinate, but whatever. Okay, so let's look at one component. So we're gonna have negative, where's my negative sign? I had my negative sign is missing on here. I guess I'll just look at this. J dot del prime, because it won't matter. X minus x prime over omega hat cubed. Now, what did I do here? Remember that omega hat is omega over omega. The vector omega over the length of omega. So I just replaced it. I replaced this guy with just omega over its length. That's why I have a cubed down here. Yeah, everybody good? This just helps me because I can, you know, mess around with stuff. Okay. And then I can now use a product rule again to write this as del prime dot x minus x prime over omega cubed j minus x minus x prime over omega cubed del prime dot j. Okay, now we're going to invoke steady currents. Okay, so for steady currents, del prime dot j is 0. Yeah. Okay. So that's good. So that gets rid of one of our terms, and I'm gonna have to get a new layer. Okay. And let's erase some of this stuff because now we're just dealing with this one term. We've already said that this guy is this, right? And so now we're dealing with this. So let's erase some of this. We'll erase all this too because we'll come back. All right, so now we're only dealing with this guy here. And we're still only dealing with one term, but if we, meaning one component, if we do it for one component, it's true for all the components. Okay. So let's think about if we now have, remember that we were integrating over volume before, right? So we'll integrate here and we'll put this term back into an integral. Make a point here. Oops, I should put this like this, J. Okay. Okay. And now I can use, this is a divergence, I can use divergence theorem. This is over a volume to say, oh, okay, I have a surface integral now of just x minus x prime over omega cubed j dot dA. Okay, but this surface can be made as large as we want because the original volume integral is only over where the current is, right? So remember, it's d tau prime, so it's wherever the current is, that's where the volume integral is, and that's not everywhere. You don't have, this wouldn't work if we have infinite. We have currents in every part of the universe, right? So let's just assume we don't. So that integral is generally just over the volume where there is current. If I raise the volume to be all space, the integral shouldn't change, right? Because there's no current outside of where the current is. So I'm going to get the same number. Does this make sense? So if I do that though, right, that means the surface is way out at infinity. And by the same argument, this is going to be 0, right? So this means that J, because J is 0 out in the surface, if the surface is out at infinity, right? J is 0, so yeah. So this is going to be 0 by that argument. All right, so what that just leaves us with this guy. This is the only term we had that survived, right? Okay, so let's go back to our answer here. I'm gonna go back, so I'm going to, let me see, I'll go to a previous layer, so because I have that already out. Okay, so here, let's duplicate this layer. It's very hot in this room, by the way. I don't think there is air conditioning in here, by the way. We're gonna be in trouble. That does not work. Yep, I know, it'll get stolen.
Yeah, but that was be.
You know it, you know they will. Okay. Okay, so we have the red term, this term is gone, yeah? This term is bye-bye. So all we have is the red term. Okay, so del cross B. Maybe I can get B and G to put a real one in because that's not working. I can call them and tell them. They've been putting air conditionings all over the place, so they must have them. That's just probably out of coolant or something. It doesn't work. Okay, mu 0, 4 pi. And then now we have the integral, right, over a volume. And then this del cross stuff is just del dot omega hat over, well, how about if I just replace that with our delta function? 4 pi d3 omega d tau, right? And so this is just going to be mu 0 times 4 pi. Oh, where's my J? I think I had a J somewhere. Yep, my bad. There's a J right here. Left him out. J. Okay. And so if it's 4 pi, u mu 0, 4 pi over 4 pi and J. Okay, love your delta functions. And so we get, again, mu 0 J, which is what the expected answer was. Okay. All right. Well, we're at 73%. We're doing good. Doing good. Okay. So in fact, the Maxwell's equation that looks like this, del cross B is equal to mu 0 J is Ampere's law. It is also a Maxwell equation, as we know. Okay, but it has a name like Gauss's law has the name, right? It's Ampere's law. Okay. So if you thinking about doing problems with Ampere's law, then we have to think a little bit about kind of the mechanics, and we'll do an example of how to do that. Let's. I'm trying to think what I want to do. So I want to give you a worksheet. Well, maybe I need to give you an example. So let's do just a current wire. We already know what B is for just wire, but we can do it with Ampere's law. We kind of already did it, but we're gonna now think like we're using Ampere's law, the way that we use Gauss's law. Okay. All right. So we're gonna use Ampere's law. To calculate B due to long wire with current I. Okay, so how do we do this? So again, we have our current, and I'm going to draw it like this. Here's I. And what we do is we put an Amperian loop, like we have a Gaussian surface, we have an Amperian loop, and we want to put it such that we have some I that it encloses, right? Otherwise, why would you do it, right? So you're going to put it kind of enclosing the current, circulating, right? Going around the current. And then you want to put the direction of your integral, or the direction of your loop of your integration around the loop, right, by right-hand rule. So in other words, if I wanted to draw my Amperian loop here, and I wanted to tell myself how to integrate it, right? I'm integrating in that direction because I'm putting my thumb in the direction of current, and my fingers will curl around the direction of integration of the loop. Yeah, okay. Because it is ambiguous when you think about it, which way should it go? But by right-hand rule, you won't make a mistake. Now, the question is this Amperian loop, and it's supposed to look like it's going around the wire, doesn't really look like that, I'm sorry. So is B constant everywhere on this Amperian loop? Because if it's not, then you have not drawn the correct Amperian loop, or maybe it's not possible to do with Ampere's law, and you got to whip out the Biot-Savart law, right? So it's again, just like Gauss's law, you can't have a surface where E is constant everywhere if you want to use Gauss's law to get the field. Similarly here, B has to be constant. The direction cannot be constant, that's fine. Okay, but it's got to be constant so you can pull it out of the integral, right? So let's write down, we usually start with the Ampere's law in integral form, which is the integral around a closed loop, Amperian loop, B dot dl is equal to mu 0 I enclosed. And if you're using like a volume current, of course, this I enclosed would be this J dot dA, right? Remember? Yeah. But we just have a regular old current here, that the current enclosed is just going to be I. We can just look at it and see that, right? Okay, so now we just got to figure out, okay, what is this? Well, so first of all, we have a distance away S that we're putting our loop at. That's where we're interested in the field. And DL will be this little vector that points perpendicular to S in this case, right? And we've said before that B and DL are going to have the same direction. Yeah, DL is in a phi hat direction, so is B. You have to reason these things with just your head. This isn't something you're getting from Ampere's law, right? You have to know what direction B is. Otherwise, we really can't use it. Similar to Gauss's law, if you don't know what direction E is, you can't really use Gauss's law to get the field. Okay. So, all right. So we know that B dot dl is just B dl because they're in the same direction. So I can write the integral B dl. Okay. DL again is going to be SD phi, right? Because it's the DL phi that I'm interested in. Yeah. And I can pull B out of the integral because it's the same everywhere along the whole integral of D phi, right? Okay. So becomes B, the integral DL, which is B, the integral SD phi. Oops, my bad. Integral 0 to 2 pi, and that becomes BS integral 0 to 2 pi of d phi, which is just 2 pi. So we get 2 pi SB on one side. So we have B times 2 pi S is equal to mu 0 I. Yeah, so B is mu 0 I over 2 pi S. And then you gotta, you don't get the direction really. You already decided what you think the direction is when you did this step, right? In the phi hat direction. Yeah, by using an Amperian loop. Okay, why don't we try, we've got a little less than half an hour. Let's try worksheet. So the first one is, there's 3 different problems here. And the first one is very similar to this one, but it's not quite exactly the same. Okay. this all about? Okay, I'm gonna stop the share now that I put the worksheet up for, one sec. Stop recording.